Hi, this is Benny. I've dedicated my life to understanding the universe in hopes that someday I am given the opportunity to hop on a rocket and see it for myself. Growing up, my safe space was between the covers of a book. My friends were people like Percy Jackson, Alex Rider, Paddington Bear, Beatrice Pryor, Hermione Granger, and the Astrosaurs, a group of crime-fighting dinosaurs in space. And so, using Space Bites, this podcast, I am hoping to create the same type of safe space where knowledge is for everyone and anything is possible. Together, we can marvel at the boundless beauty of the universe and find hope within the delicate intricacies that weave the fabric of our world. If there's one thing we have in common as human beings, it is our curiosity, and a curious mind is a happy one. Together, we will learn how the gold in our rings was made inside of stars, how the flap of butterfly wings can cause an earthquake, how charged particles from the sun interact with Earth's magnetic field to paint the sky with glowing lights, and how math is the language that describes everything. Every atom in your body was created in a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of it originated in stellar furnaces. This means that quite literally, the universe is in you. You are a product of cosmic alchemy, billions of years in the making. The same processes that formed galaxies also formed you, linking your existence to the vastness of the universe. Today's episode on the cosmic microwave background is the first episode in a series called Intro2Cosmology, a guided journey through the story of the universe, from the first split seconds after the Big Bang to the mysterious dark matter shaping galaxies today. Cosmology helps us answer the biggest questions humans have ever asked. Where did everything come from? What is it made of? And how will it all end? In this series, Intro2Cosmology, we will break down the building blocks of the cosmos, from space, time, and gravity to the expanding universe, the cosmic microwave background, and the origin of galaxies. No advanced physics required, just curiosity and a sense of wonder. Whether you're a student, a space enthusiast, or just someone who's looked up at the stars and wondered why, this series is for you. Let's unravel the universe, one episode at a time, here at Space Bites with Benny. Hello everyone, and welcome back to another episode of Space Bites with Benny. It's me, Benny, your favorite nerd. And we're going to get personal for a second. As a master's student, I'm not only learning the technical skills in cosmology or experimental physics, which is the field I'm doing my master's thesis on. I'm also learning how to grow as a person. I'm learning how to work long hours without burning out, how to let go of perfectionism that has plagued me my entire life and just ship the work, and how to create structure for myself when no one is telling me what to do. It's not easy, but these are all things that you have to learn as you get more and more into research. Some weeks, like this one, are filled with repetitive work, dense reports, and the kind of academic grind that makes the spark feel very distant. The spark that I feel for cosmology and understanding the universe we live in. But every time I sit down to write or record an episode, I reconnect with this wonder, this love, the sheer scale and elegance of the universe that pulled me into this field. These episodes that I'm making here on this podcast, Space Bites with Benny, give me space, both literally and figuratively, to remember that beyond the equations and deadlines, I'm part of something much bigger. A cosmic story, if you'd like to say, unfolding across billions of years. So this episode is for everyone who's feeling stuck, burnt out, or just tired of the day-to-day. Welcome back to the stars. Let's fall in love with the cosmos all over again. So this episode is the first in a series called Intro2Cosmology. And this episode is about the cosmic microwave background. Now, I'm going to give you 3 facts about the CMB that hopefully blow your mind and make you feel like you want to stay along for the ride, for the whole, 30 to 45 minute episode. First off, did you know that there are about 411 CMB photons per cubic centimeter? Did you know that CMB photons can also cause static on our TVs? And that the CMB is the clue which caused the Big Bang model of the universe to be favored over the steady state model. And these are all things that I'm about to explain to you. So for today, we're peeling back the deepest layers of time, back to the oldest light in the universe. And this is called the cosmic microwave background. You might have heard some people call it the baby picture of the cosmos, but trust me, it's so much more than just a snapshot. It's a frozen fossil of physics at work. It's where gravity, quantum fields, and spacetime itself combine together and help us explain or describe this phenomenon. But to better understand the cosmic microwave background, we first need to talk about light, what it is, how it works, and why not all light is visible. Let's begin with the most important player in the universe's early light show, electromagnetic radiation. So to start with, light comes in many flavors, and this is called the electromagnetic spectrum. It's not just what we see with our eyes, but it's a part of a vast family. It's a continuum, a spectrum of radiation of light that includes everything from low energy radio waves to ultra energetic gamma rays. So, what does this spectrum include? Start off, radio waves. These waves are used for broadcasting. And then you have microwaves, like the one in your kitchen, or the CMB, because that's where the name comes from, cosmic microwave background. Infrared, heat fission, visible light, this is what our eyes detect. Ultraviolet, for example, this is, sunburn territory. X-rays used in hospitals. And finally, gamma rays. These are emitted by radioactive decay and some cosmic events. So what's the difference between these different types of light? It's their wavelength and frequency. So long wavelengths equal low energy, such as radio waves, which makes sense because these radio waves, these broadcasting waves, need to be able to propagate or move over long distances, whereas short wavelengths mean higher energy, such as gamma rays. Microwaves, like the cosmic microwave background, are low energy light that our eyes can't see but instruments can detect. So it's not like you can just walk outside and look up at the sky and be able to see the cosmic microwave background. That's not to say we can't detect it, because we can, and I'm going to tell you exactly how. So let's jump into our little time machine and go back in time to the early 1800s, where there was a man, Thomas Wedgwood, and he was a British pottery maker. And he noticed something strange when observing the glow of his ceramics in a kiln. A kiln is this sort of oven thing, I guess you can say. So the brightness and color of the glow of his ceramics did not depend on what the pots were made of. It depended only on their temperature. Hotter objects, so hotter pots, glowed brighter and shifted from red to blue, while cooler ones, so the ones with the lower temperature, glowed dimmer and redder. And this was the first clue that heat and light were fundamentally connected. Later, physicists like Gustav Kirchhoff and Wilhelm Wien studied this phenomenon and proposed a theoretical object called a black body. A black body is this idealized object, I guess you can say. I say idealized because it absorbs all incoming light and emits a perfect spectrum based only on its temperature. This black body glow is what you see when you, for example, look at a red hot stove coil or the surface of the sun. So it is emitting the same amount of light that it is also absorbing. And then by the early 1900s, classical physics hit a wall. The equations that predicted that a black body should emit infinite energy at high frequencies, so emitting infinite energy at high frequencies, especially in the ultraviolet range. This became known as the ultraviolet catastrophe. Enter Max Planck, the father of quantum mechanics, in 1900s. To resolve this catastrophe, this ultraviolet catastrophe, he proposed something that at the time was pretty radical, that light energy is not continuous, but rather discrete and is emitted in tiny packets or quanta. So you can imagine these this light energy is not something continuous, or so it's not like, for example, a continuous wave, or like if you're pouring water from a bucket into a different bucket, instead of having the continuous flow of water, you're rather carrying water in tiny packets or in tiny amounts and then pouring it over. And so he introduced a new constant, H, now called the Planck's constant, because of course he would name this after himself, and wrote the now famous equation E equals to hv, or h nu, where E is energy, H is the constant, and nu is the frequency of light. With this idea, Planck did not just patch a broken theory, he started an entirely new one, and we call this quantum mechanics, which is something I'm pretty sure you've heard of. This quantum solution perfectly described the black body spectrum, and more importantly, it laid the groundwork for all quantum physics to come. It also gave us a new way to understand the early universe, which, as we will see, behaved like a gigantic black body Eve oven on a cosmic scale. So we went over this idea of a black body. We went over this idea of the electromagnetic spectrum because at the end of the day, what we're trying to do is come up with these vocabulary words and these descriptions, these topics that allow us to quantify and characterize this universe that we live in. And this idea of a black body is something that we will need to use to understand the early universe, because the early universe behaved in itself as a gigantic black body. So now imagine the early universe not as something dark and void, but as a radiant, hot, dense soup. And this soup is full of glowing plasma of photons, electrons, and protons. And all of these particles are packed so tightly that no light could travel freely. It was like looking inside of a star, but everywhere. That's how bright it was, because we all know stars are super bright. And when we say that these are all packed super tightly, it means they're colliding and interacting with each other, and there's no space for them to move freely in the universe. So this early universe acted like a perfect black body. It absorbed and emitted radiation uniformly based only on its temperature. The photons bounced endlessly through the plasma, constantly interacting, maintaining perfect thermal equilibrium. And so at this stage, the universe had a temperature of about 3,000 degrees Celsius. And the radiation within this plasma followed the black body spectrum we first learned about when looking into ovens and stars. And this wasn't just a patch of plasma, it was the entire universe glowing with the same physics. So this is not just some pottery in an oven. This is the entire universe that we're talking about. And this entire universe is glowing with the same physics. And so this light that was originally in the visible and infrared range is what we now observe, stretched by billions of years of cosmic expansion. And this is the cosmic microwave background. Fast forward to about 380,000 years after the Big Bang, the universe had expanded and cooled to around 3,000 Kelvin. So originally the universe was super hot. It was like this very dense soup full of plasma and like highly interacting particles. But as we go forward in time, the universe expands and the temperature decreases. The universe is cooling down. And finally, it becomes cold enough for free electrons and protons to combine into neutral hydrogen atoms. So these particles are no longer so densely packed together, but because some electrons and protons combine together to form neutral hydrogen, the photons, these particles of light, these quantized light particles, are able to scatter and move freely through the universe. And this moment is called recombination, even though technically it was the first time these particles combined, but the name kind of stuck. So with electrons locked into atoms, photons no longer scattered constantly. They were now free to travel across the cosmos. This transition, when light decoupled, so when light separated from matter, is known as photon decoupling. And matter can be anything from what makes up our bodies to our tables to dark matter. And the universe went from an opaque fog to a transparent sky. The light released at that moment, radiating outward in every direction, is what we detect as the cosmic microwave background. And at the time of its release, this light was initially visible and in the infrared part of the spectrum. But over the next 13.8 billion years, which is the age of the universe, the expansion of space itself, because as you know, the universe is expanding, it is not static. It stretched the wavelengths of these light particles, of these photons, and this is a process called cosmological redshift, this expanding, this stretching of wavelength of light. And so today, these same photons arrive at Earth in the microwave region of the spectrum at a temperature of about 2.73 Kelvin. And it's the cold afterglow of a once blazing universe, a snapshot of the cosmos when it first became transparent. So you might ask me, okay, this, CMB is really cool. And I mentioned before that even though you stand outside and look up at the sky, you cannot really see it. So if you want to visualize it, if you want to be a little bit creative, which is always really cool to do, what does this baby picture of the universe actually look like? And the way that I would imagine it is a static map projected onto a snow globe. So if our eyes could see microwaves, the entire sky would glow with a gentle hiss. The CMB fills all of space with a nearly uniform glow. But scientists use color maps to visualize it. So these color maps show tiny fluctuations of just about 0.0002 degrees Celsius from the average temperature of 2.73 Kelvin. So these temperature fluctuations, these temperature ripples, are just like the crests and troughs of a calm sea. In fact, if the CMB were a swimming pool, the waves would just be the height of a single atom. Can you imagine these scales that we're talking about? For example, the age of the universe being 13, almost 14 billion years old. This is a very long period of time. Or when I'm saying that the CMB, if we imagine it as a swimming pool, these tiny fluctuations in temperature are about the height of a single atom. This is crazy. These scales are insane. So let's talk about something different now. Have you ever heard an ambulance change pitch as it passes? Of course you have. And we call this the Doppler effect. It's when waves compress as a source approaches you. So the waves of the the waves of the siren coming from the ambulance compress as the siren drives past you, as it's approaching you. And the waves of the signal stretch as the siren moves away. And so light does this too. And because our galaxy, the Milky Way, is moving at about 370 kilometers per second in relative to the cosmic microwave background, this motion causes one side of the sky to appear slightly warmer and the opposite side slightly cooler. And this creates what we call a dipole pattern, a large-scale temperature difference across the sky. And a dipole in physics is just a term that we use to describe a system with two poles, hence the dipole, one high, one low. Here, the dipole isn't an intrinsic feature of the universe, but rather it is due to our motion relative to the CMB rest frame. So, relative to the CMB at rest. Now, let's talk about a characterization of the cosmic microwave background. Or actually, let's talk about the acoustic peaks. Cosmic sound waves, rather. So the early universe wasn't silent, I guess you can say. And I'm making air quotes as I say this, but you cannot see me do the air quotes. So the early universe rang with sound waves. Dense regions collapsed under gravity, but photon pressure pushed back, creating oscillations like sound in air. Oscillations, we're talking here about these waves. So these acoustic oscillations left ripples in the plasma, which froze in place when photons decoupled. Today, they appear as patterns in the cosmic microwave background's temperature fluctuations at specific angular scales, and we call these acoustic peaks. Each peak corresponds to different oscillation modes. And I'm sorry if I'm getting too technical here. Absorb as much information as your brain allows you to. So each peak corresponds to a different oscillation mode, like notes in a cosmic symphony. By studying them, scientists learn about the universe's density, expansion, and composition. Another topic we can discuss when discussing cosmic microwave background is its polarization. So because the CMB is not just temperature, it's also polarized. When CMB photons scattered off of electrons, during recombination, they became partially aligned, like light reflecting off of water. This polarization forms two types of patterns, E modes and B modes. E modes are radial or circular patterns, and they come from density waves, whereas B modes are swirly, curly-like patterns. They may be caused by primordial gravitational waves, ripples in spacetime from the inflationary epoch. And these B modes are incredibly subtle, but if we detect them clearly, it would be the smoking gun for cosmic inflation, which is proof that the universe's earliest moments were governed by quantum fields and stretching space. So how did we discover the CMB? In 1964, two research groups were on the verge of cosmic discovery. The first group was Robert Dicke and Jim Peebles at Princeton, and they were theorizing that if the Big Bang was actually real, there should be an ancient glow of leftover heat. Faint, but detectable. The other group was Arno Penzias and Robert Wilson at Bell Labs, and they were testing a sensitive radio antenna designed for satellite communications. So Penzias and Wilson encountered a mysterious background signal or noise, a hiss, consistent in all directions, regardless of the time of day or the season. And they tried everything. They recalibrated their instruments, they checked for radio interference, and they even evicted the pigeons that were nesting in the antenna, whose droppings they initially blamed. But still the noise persisted. Eventually, the word reached Princeton, where Dicke and Peebles immediately realized what they were hearing. It was in fact the cosmic microwave background, the afterglow of the Big Bang itself. And this in itself is so amazing because it's the universe communicating with us, being like, this is the afterglow of the Big Bang, the afterglow of its origin, right? There is this sort of communication happening between us and the universe. There's this CMB is, so it might be helpful to know that the CMB is as far back into time of the universe that we could look into. We can't look further back than the CMB. And so this amazing discovery earned Penzias and Wilson the 1978 Nobel Prize and confirmed that the early universe had been hot, dense, and glowing, just as the Big Bang Theory predicted. So this is not all very theoretical, because in the 1990s, NASA's COBE satellite precisely measured the spectrum of the CMB across the sky, and what it found stunned the scientific world. The spectrum that COBE, this NASA satellite, found had perfectly matched a perfect blackbody curve to better than 0.01% accuracy, and no lab experiment on Earth was able to ever produce a better match than this. And this was crucial because it confirmed that the early universe was in thermal equilibrium, a smooth, uniform plasma in perfect energy balance. It also effectively ruled out alternative theories, like the steady-state model, which couldn't really explain such a thermal spectrum. And so the cosmic microwave background became the most perfect blackbody ever observed. The Big Bang Theory now had a thermal fingerprint, and the universe passed the test. So, let's talk about tiny ripples, giant consequences, and the seeds of galaxies. Because surely some of you might have wondered, where did all of this come from? The galaxies, the planets, these large-scale structures, where did they all originate from? And the CMB has in fact provided us with this information. Because the cosmic microwave background is in fact not perfectly smooth. It has tiny fluctuations in temperature, like I told you before, about 1 part in 100,000. And these are not random. They're the first seeds of cosmic structure. So can you imagine now that this cosmic microwave background, this last scattering of light that the universe provided us with, has tiny fluctuations in temperature, and these tiny fluctuations in temperature are not random, but in fact were the first seeds, like a plant, how a plant has a seed and grows into something larger. These tiny temperature fluctuations were the first seeds of cosmic structures like galaxies. Small overdensities in the early universe meant slightly stronger gravity, and over time, these tiny differences pulled matter together. So you had overdensities, so you had more matter. More matter had stronger gravity and thus kept pulling in even more matter over time. And this eventually formed galaxies, clusters, and cosmic filaments. These are all large-scale structures that are in our universe. And you might be surprised by this because maybe you thought that the universe was only, stars, planets, it's only what our solar system entails. But in fact, it's so much more than that. And so the 3 key physical effects left their mark on the cosmic microwave background. And feel free to research more into this if you're interested. The first was the Sachs-Wolf effect. The second were these acoustic oscillations that I already talked about. And third is the silk damping. And silk damping is the photon diffusion that was smoothed out the tiniest fluctuations. And so these ripples, these fluctuations in temperature, are like gold mines for us cosmologists. They tell us about the matter content, so what our universe is made of, the expansion rate, how fast is our universe actually expanding, and tells us about the history of the universe. And I really hope that as you listen to this episode, you really understand that the universe is so much more than we originally thought. There's so much happening out there that we still don't understand. And looking at only one thing like the cosmic microwave background, already we were able to understand and learn so much about the early universe, which is such a mystery because it's like looking back in time. It's a form of time travel, or at least I'd like to think that it is. And so the CMB, the reason why I wanted it to be the first part of the series is because really it's like the universe's blueprint. It helps us decode what our universe is. So when we map these tiny temperature fluctuations in the cosmic microwave background and analyze them statistically, we produce something called a power spectrum. And now we're getting very technical. A power spectrum is just a graph of how these fluctuations vary with angular size. And the power spectrum is like the fingerprint of the universe's initial conditions. So initial conditions being what was the universe like very early on, like in the beginning. So acoustic oscillations, I want you to imagine them as these sort of, kind of looking out into a wave, right? You've got all these like different peaks and troughs. And so these acoustic oscillations are just peaks. So obviously there are a lot of peaks, but we will focus on only the first three. And so what do these three peaks tell us? The first peak tells us that the universe is flat, or can be approximated as flat. The second peak tells us how much normal matter is present. So as you know, we have normal matter and we have dark matter. So the second peak in this power spectrum of this cosmic microwave background tells us how much normal matter was present. We also call this normal matter baryons. And the third peak hints at the influence of dark matter. Each feature in the spectrum matches a physical process from the early universe, and these measurements are made using ultra-sensitive telescopes and satellites like WMAP and Planck, which can scan the sky for temperature and polarization variations across different angular scales. Scientists then use sophisticated statistical tools to analyze this data and generate the power spectrum. The power spectrum being these peaks. These peaks are what give us this information about the universe's initial conditions. Now, let's talk about polarization, which we already kind of did in the beginning. E modes and B modes. These allow us to hunt for primordial gravitational wave, which have not been detected yet. Primordial gravitational waves are ripples in spacetime generated during inflation, where the universe expanded faster than the speed of light. I'm going to say that again. Primordial gravitational waves are ripples in space-time generated during inflation when the universe expanded faster than the speed of light. Mind-blowing. Detecting B-mode polarizations, which are these like swirling curl-like patterns, is like hearing the gravitational echo of inflation. It's difficult, but if observed, it would be a direct signature of the quantum origins of space-time itself. Because when we talk about inflation, we start talking about quantum fields. And we start talking about quantum fluctuations that were origins of, they were the origins of structures in the universe. So let's talk a little bit about inflation, the quantum origin of everything. Because the second part in this series is going to discuss this mind-blowing exponential expansion of the universe that happened at the speed of light and happened in the first trillionth of a second after the Big Bang. And inflation theory explains why the cosmic microwave background is so smooth and yet contains tiny fluctuations, these temperature fluctuations that we discussed before. During inflation, during this exponential expansion, tiny quantum fluctuations in the inflaton field, which is what we call this quantum field of inflation, were stretched to cosmic scales. So you had these tiny quantum fluctuations, these tiny seeds, and over time, due to this exponential expansion, were stretched to cosmic scales. These fluctuations became the seeds for galaxies, stars, and cosmic structure. The larger structures in the universe can be traced back to these quantum fluctuations, smaller than atoms. In the CMB, the cosmic microwave background is our best evidence of the staggering connection between quantum mechanics and cosmology. And now we reach the end of our episode. The CMB as a time machine. It is more than ancient light. It's the closest we can get to seeing the early universe directly. It's like pulling back a curtain and being able to look into the early universe. It tells us that the universe had a hot, dense origin, that quantum physics shaped the cosmos, and that structure, galaxies, and stars grew from tiny ripples in that ancient light. And in fact, this is just the beginning. I hope that I captured your curiosity, because next time we will explore cosmic inflation in more depth, how the universe might have burst from nothingness, and what that means for the multiverse, quantum fields, and whether we're alone in the cosmic phone. Until then, keep looking up, keep wondering, and stay curious.